Hi guys. So today I want to talk about American options on non-dividend paying stock. So let's assume that we have a function h of x and this function is a convex function. It's non-negative and h of 0 is equal to 0. Okay, so it can be any convex function that basically satisfies these three properties. Now I want to consider an American option, okay, such that whenever we exercise the American option, okay, the payoff is given by h of s of t. Okay, so we are assuming that we have an American option on a stock, and whenever we exercise the option, you remember when we exercise the option, we get the intrinsic value. So this would be intrinsic value. Okay, whenever we exercise the option, the value of the option or the intrinsic value is given by h of s of t. And what I want to show you right now is that the discounted value of the intrinsic value is a submartingale. Okay, so we have a function which is convex, non-negative, h of 0 is equal to 0, and the intrinsic value of an American option, which is the amount of money that we get if we exercise the option at any point in time, is given by this convex function of the stock. So we are assuming that we have an American option on a stock. Okay, we haven't really talked about what kind of an American option it is. We're just saying that the payoff of the American option is some convex function, okay, without specifying really what the payoff is. And I want to show you right now is that the discounted value of this intrinsic value is a submartingale. So if you remember what we mean by a submartingale, if this is a submartingale, let's assume that 0 is less than equal to u less than equal to t, right? So we, under the risk neutral measure, a submartingale would mean e to the power of minus rt h of st given information at u is greater than equal to minus ru h of su, right? So submartingale has a tendency to rise. Okay, so this is a submartingale. So right now I want to show you that this holds true. Okay, when for an American option the intrinsic value is given by h s of t, where h is basically a convex non-negative function. Okay, so let's prove that this is a submartingale. Okay, so in order to show that the discounted value of the intrinsic value of an American option for a non-dividend paying stock is a submartingale, let's start by first understanding what a convex function is. So if I draw a convex function here, let's assume that this is x1, this is x2, x1, x2 both are greater than 0, and this function is h of x. Okay, for this to be convex, what we need is, if we take a linear interpolation of these 2 points and we define another point x star, and let's assume x star is nothing but 1 minus lambda x1 plus lambda of x2, okay, then we want to show that h of, or if the function is convex, then we know that h of this point, which is 1 minus lambda of x1 plus lambda x2, which is this value right here, okay, the value of the function h at this point, and this point is given by a linear combination of x1 and x2. Okay, this is going to be less than equal to, now if we take a linear combination of 1 minus lambda value of the function at x1 plus lambda value of the function at x2, okay, linear combination of this right here. So a convex function basically means that this is going to be less than equal to this point. This value is going to be less than equal to this point. Okay, so that's what we mean by a convex function. Okay, now further, let's assume here that x1 is equal to 0, x2 is equal to x, and h of 0 is equal to 0. Let's substitute these values here. If we do that, we'll get x1 is equal to 0, so this goes away. Instead of x2, we'll write x, so we'll get lambda x. Okay, and here we are assuming that lambda is a number between 0 and 1. Okay, so on the left side, we get h of lambda x is less than equal to, now this is h of 0, which is 0. So here we get lambda h of x. So by a convex function, we mean that this inequality holds true. Okay, as I've shown you right here. This is what we mean by having a convex function, and substituting these values here, I'll get this. So this inequality holds true for a convex function. Now further, let's assume that 0 is less than equal to u, less than equal to t, less than equal to capital T, or u is less than t. Okay, in that case, lambda can be written as e to the power of minus r t minus u, right? Because this u is less than t, so this number would be between 0 and 1. So now what I want to do is I want to substitute the value of lambda right here and take conditional expectations on both sides. Okay, so let me do that. So I'll get expected value under the risk neutral measure, h, instead of lambda I'm going to write e to the power of minus r t minus u. Instead of x, now I want to substitute s of t. Okay, h was a function of x. Now instead of x, I want to write s of t. Okay, and I want to take conditional expectation at time u. And from here, I can see that this is less than equal to lambda. Expected value under the risk neutral measure of lambda is e to the power of minus r t minus u h of st, given information at time u. Okay, so this result comes straight away from here. Instead of x, I'm writing st. Instead of lambda, I've substituted e to the power of minus r t minus u. This is what I'm going to get. Now, in order to, I can apply Jensen's inequality here, because this basically is a convex function. And from Jensen's inequality, I can write this as expected value under the risk neutral measure of h e to the power of minus r t minus u s of t. Okay, given information at time u. This can be written as, this is greater than equal to, according to Jensen's inequality, expected value, h of expected value of this thing, e to the power of minus r t minus u st